Hello students, today I am starting with astable and monostable multivibrator. Let's see the aim of the experiment to design monostable and astable multivibrator. Components required: IC 555 timer, resistor, capacitor, power supply, functional generator and CRO. So first the theory. So what is this astable multivibrator? So astable multivibrator is also called as free running multivibrator because it doesn't have any stable state. That means it keeps switching between one state to other state by itself. That's why it will be called as free running multivibrator also. Next, what is this monostable multivibrator? Monostable multivibrator has only one state. Normally in this multivibrator is in stable state when an externally triggering pulse is applied. That's why in the case of monostable we are going to use external triggering from an function generator. But in the case of astable, we are not using any external triggering circuit. That is nothing but functional generator. It cannot, because it cannot remaining in any of the state. It will just goes on switching in the case of astable multivibrator. But in the monostable, it will maintain in a one stable state. So in order to do so, we have to connect to an external triggering pulse. Okay, so in order to start with the astable multivibrator, we have three cases. Let's see what are those three cases. So these three cases we will be taking with respect to duty cycle. So the duty cycle will be equal to 50% and greater than 50% and less than 50%. We have three cases with respect to duty cycle. So those I already told, that is greater than 50%, then less than 50%, and next is equal to 50%. So what is this 50%? So as you can see in this figure in the waveform, this is a complete signal. That is, when you combine T on plus T off, it is a complete total period, time period, total time period. So whenever the T on, so suppose if I take the total time period has 1 millisecond. So if I take total time period has 1 millisecond, so this T on, if it is greater than T off, that is, if you take total time period has 1 millisecond, so if it is both the T on and T off are equal, means the T on will be equal to 0.5 millisecond and T off will be equal to how much? It is also 0.5 millisecond. So if it is so, the condition is shown. So we will tell that has a duty cycle as an equal to 50%. Okay, when both T on T off are equal. Suppose this T on is of 0.6 millisecond and T off is of a 0.4 millisecond. If you add this 0.6 and 0.4 millisecond, you will get 1 millisecond. So then here you can observe T on is greater than T off. When T on is greater than T off, then we'll be calling as a duty cycle greater than 50%. So the next is whenever the T on, okay, so observe just T on, it is of 0.4, okay, then T off is of 0.6. So as you can observe that now the T on is of 0.4, whereas T off is of 0.6. That is, T on is less than T off. Then we will be taking the duty cycle is less than 50%. So we have to see all these three cases by indicating. This will be indicates that the duty cycle indicates that T on is less than T off or T off is less than T on by considering what total time period. So I just considered it as 1 millisecond. So by just how will be managing that 0.5 millisecond or 0.6, 0.4 or 0.4, 0.6. So in order to get these three cases, by choosing proper value of RA and RB. By designing the proper value of RA and RB, so we are going to maintain these three cases. Let's see how we will be maintaining these three cases. So here we're not using any signal generator. As I already told, in a stable asymmetric multivibrator, we are not using any signal generator. Why it is? We don't need any external triggering pulse, as the state will be switching over between one and another. Okay, so it is goes on changing. That's why we are not using. So let's see the circuit diagram. So here in the stable multivibrator, okay, it is called asymmetric. So asymmetric is nothing but this T on and T off are not equal. So maybe T on is greater than T off, or T off is greater than T on. That's why it is called as asymmetric multivibrator. So by choosing the proper value of RA and RB, as you already studied this in the theory. Okay, so what is the stable multivibrator and why we'll call IC 555 means, so in the internal structure of IC 555 timer, we are going to use three resistor of 5 kilo ohm. That's why it is named as IC 555. Okay, IC 555. So for your syllabus, you will be having the multivibrator using ICs. Okay, so let's see the we are using VCC 5 volts, the resistance of 5.6 kilo ohm and 4.7 kilo ohm. Why we choose these resistance? We can go through the design. Okay, so by designing the proper values, then hence we will be choosing the resistance A and B. Then the capacitor of 0.1 microfarad and 0.01 microfarad will be used. And mainly we will be concentrating on this 0.1 microfarad because this will shows the charging and discharging. So this RA and RB is dependent. So through this only current will be flowing. Then the capacitors will be starts charging. So that's why we are mainly depend on RA and RB, and the explanation or working you already studied in detail in the theory. So let's see. And this is the output is taken across a pin number 3, and this VC is taken across here either in a 6 pin or in the second pin. So this is the charging and discharging, charging and discharging. As you can observe here, I'm taking T on is greater than T off because here it is long, or the time taken is more when compared to T off, it is less. Okay, so let's design. So here the design we are giving, let T on is zero point 0.7 millisecond and T off is 0.3 millisecond. Okay, so that means the total period is always equal to T on plus T off. So what I am taken T on as, we are taking a T on has a zero point 0.7 millisecond and T off has 0.3 millisecond. So totally how much we are taking the T? It is nothing but 1 millisecond we are assuming. So my intention here, the duty cycle, we can call the duty cycle is greater than 50%, isn't it? The duty cycle I'm taking for greater than 50%. So in order to achieve greater than 50% case, we have to design this resistance. So this value you already studied. So the frequency, the formula, that is T on equal to 0.693 RA plus RB into C. So the T on value, we assume it has a 0.7 millisecond. So write it down here, and 0.693 into RA plus RB into the capacitor value. As I already told, mainly we depend upon this capacitor, that is this 0.1 microfarad. So that's why I'm taking it as 0.1 microfarad. Okay, so then after substitution we'll be getting 10.10 kilo ohm, that is the sum of RA and RB. But we are, my intention is to get RA and RB. So one more formula I have for T off, that is 0.693 into RBC. So we know the value of T off, or T off is nothing but it is point, how much it is, 0.3 milliseconds. So when it is a zero point 0.3 millisecond, just substitute the value of T off and 0.693 the capacitor value, then you will be getting the RB and 4.329 kilo ohm, and it is approximately equal to 4.7 kilo ohm. So we are choosing 4.7 kilo ohm. So the next is the RA. By substituting RB value, that is 4.7 kilo ohm, in the above equation. So where here we are substituting the value of RB as 4.7. So if you substitute the value of RB, so you will be getting the value of RA. So now the RA is of 5.6 kilo ohm and RB is of 4.7 kilo ohm. So then you just take RA as 5.6 and RB as 4.7 kilo ohm in order to get the duty cycle of greater than 50%. Okay, if you want the T on, that is duty cycle less than 50%, means what you have to do? You have to take the T on is less than T off. Okay, so this condition is for duty cycle greater than 50%. Suppose in the examination, the examiner may ask, design the value for duty cycle less than 50%. So when they ask duty cycle less than 50%, you just take the T on as zero point 0.6, or they may tell you take T on as so in the examination, they may ask you to choose the show the duty cycle less than 50%. At that time, you have to take T on is less than 50%. That is point. Suppose if I take the T on has suppose the examiner may uh, ask you to show the duty cycle less than 50%. So when they ask to show less than 50%, you have to take the T on has zero point 0.3 millisecond. Okay, so you have to choose the point T on as zero point 0.3 millisecond. Sometimes they only tell take T on has zero point 0.4 millisecond. Okay, so then when you take T on as zero point 0.3 millisecond, you have to take T off as a zero point 0.7 millisecond. If they tell zero point 0.4 for T on and zero point 0.6 for T off, just you substitute this value in the formula and just get the value of RA and RB, and the same RA RB you will be using in the circuit. So here the T on and T off, so it is varying, that is T on is greater than T off. In this case T on is less than T off, so that's why the circuit is called as a stable asymmetric multivibrator. Okay, so once you get the value of the RA and RB, so now we are going to see the waveform. This is the design. Okay, so similarly, next is symmetric astable multivibrator. Why it is called symmetric? I already told. When the T on and T off are equal, that time we will be telling it as a symmetric. Asymmetric means either T on is greater than T off or T off is greater than T on. So here in the symmetric, both are equal, as you can see in the waveform. So here again the RA and RB are equal. So why it is so? You are achieving the equal value. So you have to get T on and T off are equal. So that's why in the design we assume the total time period has 1 millisecond, and here the total time period is given by T on plus T off. Then the T on is 0.5 millisecond and T off is also zero point 0.5 milliseconds. So by substituting the values, so you will be getting the RA has 7.21 kilo ohm and RB has 7.21 kilo ohm, and we will be choosing it has 6.8 kilo ohm. So by then you will be taking those resistance, and this will be connected with a diode. Okay, so once you done with this, So you can observe the charging time and discharging time are equal. So when it is the output, the T on is there, then only the capacitor charges. When it is off, the capacitor start discharges. Similarly, for the next cycle, the capacitor is charging in on time and discharging in off time, and both charging and discharging of the capacitor is equal, and that will be taken across sixth pin. We'll be taking across the sixth pin at this in order to get this waveform. Okay, so similarly in the stable asymmetric also, you can observe the T on is greater than T off. So the charging and discharging time, the whenever the it is on, during on time the capacitor starts charging. When it is off, capacitor start discharging, and the charging time is greater than discharging time. As you can observe, next also charging time is greater than discharging time. Suppose if you take T on as less than T off, then the charging will be less than discharging. So this is about a stable multi-vibrator.
So next we are taking output across the third pin. Here you can see the circuit across the third pin we are taking output, and in order to see the charging and discharging we are taking across the sixth pin. Okay, so in order to see the capacitor charging and discharging, as I already told, I am designed for the T on is greater than T off, and we are achieving the duty cycle of 70% here. Okay, it is greater than 50%. So let's see the 5 timer. Okay, so here I am going to connect the 4th pin and 8th pin to the dual power supply, DC power supply with 5 volts. Okay, so it is connected, and two resistors of 4.7 and 5.6 kilo ohm is connected as shown in the circuit, and the zero point 0.1 microfarad and zero point 0.01 microfarad capacitor is connected, and we are taking the input at pin number 3. Okay, pin number 3, and the capacitor charging and discharging across the pin number 2. Okay, so the stable asymmetric multivibrator will be the T on is greater than T off, or T off is greater than T on. So from this we are going to show. Okay, so when I connect the output across pin number 3, we are going to get this. So you observe here the on time waveform. So here you can see, so here the T on is greater than T off. So what is the T on value? It is almost, you can observe, it is almost, it is of 1.3. It is almost 1.3, and it is almost 0.6 or 0.7. Okay, 1.3 into what is the time scale? So you can see here it is of 0.5. So 1.3 into 0.5 millisecond, you are going to get approximately 0.65 millisecond, or approximately 0.7. Similarly, T of how much we got? It is of 0.6 or 0.7, isn't it? Into 0.5 means you are going to get some 0.3 millisecond. So what we are designed? So this is a theoretical value we designed, and the practically we are getting some of 0.65 and one is 0.25 milliseconds. So this is about the astable asymmetric multivibrator. So next is a symmetric astable multivibrator. So in symmetric astable multivibrator, I already told both T on and T off are equal. That is 0.5 millisecond, 0.5 millisecond. So in the astable multivibrator, we are not using any triggering because it is changing between two states. It doesn't have any stable state. So here you can observe we are using two equal resistance, which I already told in the design only. So equal resistance we are using, and two capacitors of 0.1 and 0.01 microfarad is connected to the triple five diode is connected, and we are taking the output across pin number 3. You can observe pin number 3, and across pin number 2
or pin number 6, you can observe the variation of capacitor. Either the charging or discharging signal can be viewed across the pin number 2. This is across pin number 3. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So anyhow, this 2 is a variation of the capacitor. This 3 is the output. Okay, or 2 and 6 will be an triggering. Okay, so this we are not triggering any input for a stable multivibrator. Let's see how we will be getting the output. So before that, so here you can observe we are connecting to the PC. So that is for dual power supply of 5 volts. Okay, so it is of 5 volts. We are so dual power supply of 5 volts. We are connected to the circuit across pin number 3. We are taking the output. So this is your output. So here this the output across pin number 3, and this is the output across pin number 2, which is showing that charging and discharging of the capacitor. So here as you observe, the whenever the multivibrator is on, at that time the capacitor will start charging. Whenever it is off, the capacitor will start discharging. So this time off time, you can observe it is discharging. So and on time and off time are equal. So let's see how much it is. So it is almost the T on time is of 1.2 and T off time is also 1.2. So 1.2 into the scale is time scale is zero point 0.5. So that is nothing but 1 by 2. So wow, zero point 0.5 into 1.6. Similarly, 1.2 into zero point 0.5 is also 0.6 milliseconds. So zero point 0.6 T on is and T off are equal. So this will be depend upon the total period what we are taking. So the charging and discharging are equal.